All right, welcome back, folks. We're continuing to talk about probability here. We got our old friend, the normal curve, in the back. And in the prior couple of videos, we introduced some basic rules of probability and started talking about calculating probability, not just for individual events, but for consecutive events, that cumulative probability. We related that to the idea of drawing multiple samples over time. Here, we again are going to connect probability with some aspects of samples here using z-scores to talk about how we can place not just individual scores but sample means on a normal curve and how we can calculate the probability of those placements using relative standing. So let's jump into it. So again, we see down here kind of a more readable version of the normal distribution I've got over here. And again, because the normal curve is standardized and as we've already seen, very specific percentages of the population will fall within different ranges of z-scores or above or below a specific z-score. Again, we can use that to just take a z-score that we're interested in or a percentile we're interested in and make very precise calculations regarding where that would fall in the distribution. So here's the thing. Any frequency distribution can also be a probability distribution. Remember, the probability is just a measure of relative frequency. So how frequent or infrequent things are also reflects the probability that you would find a score from that group at random. So for example, the probability of a score falling between the mean down here, well, let me point over here, the mean and two standard deviations below the mean would be 34 plus 14 or 48%. That's the frequency of that score. 48% of the population is in that range, which also means that it's the probability of drawing a score from random. If I pulled a score at random out of this population, there would be a 48% chance it would be between a z-score of 0 and -2. And the same 48% chance, because it's symmetrical, between 0 and +2. So you can look at this and you can answer questions either very precisely using the normal curve table or using software, or it's kind of a ballpark using this sketch. We're going to do the latter. And we can say, what's the probability that a score that you drew at random from this population would be more than 2 standard deviations from the population mean, from that dead center? Well, you say, okay, look in here. 1, 2. About 2% of people are more than 2 standard deviations above the mean, and about another 2% of people are more than 2 standard deviations below the mean. So collectively, that's 4% of the population, which means the probability of drawing a score at random that's that far away is about 4%. So again, we're using those characteristics now to make very precise statements of the likelihood of different scores. It's just taking the same numbers, the same frequency proportions, and describing them as percentages. There's no math, there's no conversion. It's just the same numbers being described as probability rather than relative frequency. So, same deal. What's the probability that a score is between -1 and 1 standard deviations from the average? I'm going to pause, see if you can think about that. What you should be doing here is taking the percentage of scores between the mean and 1 standard deviation below average. That's 34%. If you can't see it on my board, look at it on the screen. Another 34% between the mean and 1 standard deviation above. So collectively, there's about a 68% chance that a score drawn at random will be between 1 standard deviation below and above the mean. So again, this is true no matter what the original variable was. If it follows a normal curve, those same probabilities are going to be in effect. Okay, so we're going to close things off here by introducing our next problem and starting to briefly talk about how we're going to solve it. So remember, in the last module, we used those z-scores. We wanted to look at the relative standing of single scores, where it fell relative to the mean of its distribution. Then we started doing things like taking proportions of scores above and below that z-score. But it's always been single scores. We never really care about single scores in research. What we generally care about are the averages that come from our samples that we draw. So what we can do is we can use the same process. We can use z-scores and that normal curve to show the relative standing and also the probability of the averages of different samples. So this is what we really want to do. We aren't really going to want to look at individual scores. How does this work? How can we use the same process for sample means? Well, there's a hurdle that we have to get past first. Remember when we talked about variability? We talked about the idea of using scores from a sample to estimate a population mean, a mu, that symbol that we care about, that population mean. We said, hey, the mean of our sample is going to be inaccurate overall. It's probably going to be at least a little different from the population mean, but the way we make it more accurate is we just measure more people. So the more people you measure, the closer your sample means get to your population mean. The fewer people you measure, the farther away it tends to get, the more variable it is. Scores or sample means get more volatile. They tend to vary more from the true population mean than they do with a larger sample size. So as n increases, as the number of scores you get goes up, your sample mean will on average get closer and closer to the population mean. It won't vary by as much. An easy way to think of it, imagine you measured every single person in a population. The mean of that sample would be exactly the same as the population mean because everybody's in there. Now imagine your sample is everyone in the population minus 1. Now it's maybe not going to be exactly the same as the population mean, but the mean of that 99-person sample is only going to be a tiny bit off, if that. Now imagine you lose 10 of the people in your population from the sample. Again, going to be a little more fluctuation, so on and so forth. Basically, by thinking about it in the opposite direction, if we have every score, then our estimates are perfect. If we only missing a couple scores, our estimates will only be off by a little bit. The more people you lose from the population, the more erratic and volatile those scores get. So long story short, you measure more people, your sample means become more accurate. There's less variation there. So anytime you have a sample larger than 1, and you're taking the mean of that sample mean is going to be closer on average to the population mean than individual scores would be. So the more people you measure, the more accurate these sample means become. The bigger the sample mean, the lower the deviation from the smaller sample mean. Basically, they become more accurate estimates of the population mean as you get more scores, as you measure more people. So what does this mean? We have to account for this fact because remember, a z-score includes a measure of variability. It's how many standard deviations from the mean you are. Here, what they're saying is that variability tends to drop as we measure more and more people. We have to account for that mathematically. Here's how we're going to do that. First, we get our answers to this question. How do we change our calculations for sample means compared to individual scores and sample means of different sizes? How do we account for that? We create what's called a theoretical distribution. Again, a theoretical distribution is a distribution whose characteristics are derived from higher math that is beyond the scope of this class. And we look at, again, what characteristics that distribution has. We don't worry about the proofs behind it. We just talk about what it tells us. So here's what this theoretical distribution is. It's called a sampling distribution of means. Basically, the idea is this. If you were drawing from the same population over and over and over and over again, samples of the same size of the one that you've actually got. So say you drew a sample of 100 people. The sampling distribution of means would be the answer to the question, what if you drew just an infinitely high number of 100-person samples all at random, all out of the same population, over and over and over again? What would happen? Well, it's basically saying if you took the means of all of those samples, that infinite 100-person samples that you drew, and put them all in a distribution, a frequency distribution, what would it look like? What shape would it have? So this is oftentimes called the sampling distribution because you can make a sampling distribution of variances or standard deviations, but nobody ever does that. You only really do it for means. So we just call it the sampling distribution generically, but it's that idea. We're constructing a distribution of outcomes based on random draws of samples that are the same size as the sample that we got, all drawn from the same population. This gives us context to figure out the relative standing of our own sample. So we're going to get in depth on the sampling distribution in the next video. I'll tell you in advance, it's a little bit complicated conceptually, but it's very, very simple in terms of how it affects our calculations. I'll see you there.